All right, last time we started our last section, 5.2, we took a look at multiplication of integers and some properties, some models. And today we're going to continue that. With division. I think, did we do this one right here last time? No, okay, then integer multiplication theorems. I should have done that one. My apologies. Okay, so to start with some integer multiplication theorems. For every integer, a, if you multiply a by -1, it simply changes it to be -a. And if it was already negative, then if you make it -a or the opposite of a, of course, it becomes positive. So multiplying by -1 changes our signs, positive to negative, negative to positive. Theorem 5.7 is almost like your associative property, that first one. You have -a times b, and that's actually the same as the opposite or the negative of a times b. So you can sort of do the negation second and do the multiplication first. -a times -b is actually ab. We saw another way to think about this last time, I believe, or maybe a couple times ago with absolute values, but this one actually is another option of how to think about it. And then theorem 5.8 is the distributive property for subtraction. If you have a times b minus c, it's ab minus ac. Of course, you see the a distributing through. And then if you have b minus c times a, we can also distribute in this order. So we have ba minus ca. All right, and then we have division. Much like when we defined subtraction, we define division in terms of its opposite operation, multiplication. So for all integers a and b, a divided by b is the unique integer c, if it exists, such that a equals b times c. And this is very much like when children first learn to do division. They're relying heavily on their facts that they know about multiplication. For example, 15 divided by 3 is 5, and the way that we would think about that is if you said 15 divided by 3, the question would be, what do I multiply 3 by to get 15, right? And a child should know their multiplication table by threes if they were working with division, and be able to answer 5 based on prior experience, prior knowledge. So if you're thinking about how I describe this in terms of being written down, 15 divided by 3 is equal to 5, and of course the reason is because 3 times 5 equals 15, and you'll hear these referred to as a fact family. Chapter 4, which is also on your test, chapters 4 and 5, talked about divisibility, and it talked about divisibility as in, it divides without a remainder. You guys know what I'm talking about, right? So like when we talked about 2 dividing 12, it's because 12 divided by 2 is a whole number. We have the same kind of idea when we work with integers. So we can talk about divisibility for integers. So a divided by b is a unique integer, or if it is a unique integer, then a is divisible by b, or equivalently b divides a. And we see that same notation we saw back in chapter 4. You've got the b, you've got that vertical bar, which is read as divides a. And it means it is a divisor for it, evenly goes into those kinds of descriptions. We saw inequality notation also with whole numbers. It's not any different here either. For all integers a and b, we say that a is less than b, if and only if there is a positive integer k such that a plus k is equal to b. We did it for whole numbers. We can do it for integers. The reason that -5 is less than -3, for example, is because I can actually add something to -5, and it'll equal -3. What would I have to add to -5 to equal -3? 2. And if there's a number that I can add in there, that number k has to be positive, right, for this to make sense. If I added in a negative, this wouldn't be true. So a positive number that I would be adding in there, then I would equal each other, and so that's what it means to be less than. All right, a bit of notation. Theorem 5.9 talks about how we can think about less than. So for integers a and b, a is less than b, or equivalently, b is greater than a. If and only if b minus a is equal to a positive integer. That is to say, b minus a is greater than 0. If I take a big number minus something smaller, I should get something left over, right? So if I'm talking about I'm going to eat 1,500 calories today, and I ate 852, and I subtract those, I still will end with a positive number left over. So that's why 1,500 would be greater than 852. Right? When I subtract them, I get a positive number. Interesting things happen with inequalities and multiplication, though. So if we have a is less than y, I'm sorry, not a, x is less than y, and we add a number to both of them, the inequality stays the same. Whoops. There we go. So if x is less than y, then x plus n is less than y plus n. And it doesn't matter what n is. N can be positive or negative. All right? And the way I always think about it is in terms of heights. I know that technically works just for, it's a positive number description, but it works the same way. If I stand up here and Cameron stands beside me, Cameron, you're taller than I am. So if I add 3 inches of heels to my feet and you add 3 inches of heels to your feet, you're still taller than I am, right? That doesn't change. The inequality stays the same. So no matter what I want to add or subtract, or if, we were to be standing on steps and then we both stepped down 3 steps, we would decrease our values both by 3 steps, whatever that distance would be, we would still have Cameron taller than me, all right? So that's this first one. If I add or subtract a value, then the inequality is the same inequality. The next one talks about what happens when I multiply by a negative. And I want to describe why this works, but if x is less than y, and I multiply them both by a -1, the inequality actually changes direction. So I actually end up with negative x is greater than negative y. And I'm just going to show you an example with numbers to show you why that makes sense, because numbers make sense of it a lot easier. So let me do -1 is less than 3. So you guys agree with that statement, right? Sure. And if I multiply them both by a -1, then -1 times -1 is +1. 3 times -1 is actually -3. Which of those numbers, 1 or -3, is bigger? Well, the 1 is, right? And if you take a look, then the inequality, in fact, changed. That's not really a proof. Proof by example is not really a thing, but it certainly seems reasonable with that justification, and it is a true statement. It's true all the time, okay? So you multiply by a -1, and it changes the direction of the inequality. If you multiply by a number bigger than 1, so like on the third sum it says x is less than y and n is greater than 0, then if you multiply x times n and y times n, the direction of the inequality stays the same. Okay? It's like saying if I spend 4 hours studying for a test and Samantha spends 6 hours studying for her test, then Samantha's number is bigger than mine. But if we both doubled the amount of time we spent studying, she's still going to spend more time than I did studying, right? If you double something or you triple something or whatever, the inequality stays the same. If it's a negative, however, it switches. So if I multiplied by any other number that was negative, I would end up switching the order of the inequality. And I know we did it for an example of the -1. It works for any negative number, though. So let me just use the same example that I had before, and we'll multiply by 0.5. I know we haven't worked with decimals in this class, but I think you guys can handle it. So if I multiply -1 times 0.5, I have it was supposed to be -0.5 is what I meant to do. My bad. -0.5. If I multiply -1 by -0.5, I have a +0.5. And if I multiply 3 by -0.5, I actually have -1.5, -1.5. Well, the positive number is bigger than the negative number. And this works the same way if they were both negative or if they were both positive, the same direction. Everything would work just the same way. There's nothing special about the fact that I happen to choose a negative on the left and a positive on the right. That's not unique to something going on, okay? So So if I multiply by a negative anything, -1, -1/2, -372, the direction of the inequality changes. All right, the last thing that we're going to take a look at for this semester is a little bit of solving equations. There's nothing that we're going to do that's super like college algebra-y. That's not what we're looking at. But solving equations happens in about 5th grade these days. You guys are going to be certified up to, those of you who are doing elementary education, right, certified up to 8th. Am I right on that? So 5th grade certainly in that sort of ballpark. And even if you're like, no, I really don't want to be at a middle school, 5th grade's usually in an elementary, and if you are dead set on being in a specific elementary, you might choose to teach a year in 5th grade so that you can teach the next year in 1st grade or whatever. So this is still within the realm of like possible in your world, even if you want to teach the little ones. We're going to use properties that we've been using for multiplication and addition, subtraction, division, all those properties to solve these equations. So we're taking a look at the first one, part A, and it says -5 times x minus 3 equals -5. And there's a couple of different things you could do to start. So would somebody like to give me a suggestion of how you might start this problem? Distribute sounds great, and we have a distributive property. In fact, we looked at the distributive property for negatives today. So if we distribute this, Samantha, you were the one who told me to. Do you want to tell me what I'm going to get?
-5x plus 15.
Fabulous. And you even remember to do the plus 15. Common mistake, right? I have a negative and a negative, so I get a positive. All right, so someone other Samantha, what would you do next? Cameron wants to subtract the 15, and if we do it to one side, we have to do it to both sides, right, Cameron? Yeah, and it's the same idea as like my height example, where we both have 3-inch heels on, it stays the same, right, the distance between. So on the left-hand side, these add to 0, so I have -5x. What is -5 minus 15? That's integer subtraction. -20. Okay, so somebody knew. What would you do as your last step? Divide by -5, exactly. Okay, so I have x on the left, and again, now this is integer division. What is -20 divided by -5? It's 4. And it's positive, right? A negative divided by a negative is just the same as a negative times a negative. It's a positive. All right, cool. So my answer would be x equals 4. Nicely done. B is interesting. There's several things you could do on this problem. So I need a suggestion. What would you like to do? Square root both sides is one possibility, okay? Might be a little bit above what your kids would do at this age, but then again, squaring them out would probably be above what they would do as well. So square root's a perfectly a legit operation. The catch when you square root that you need to remember is that when you take a square root, it's positive or negative what you had before. So for example, I'm going to give you a simple one. If you had x squared equals 25, what two values could x be to make that work? 5, as in 5 squared is 25, or -5, because -5 squared is also 25. Do you guys see that? So that happens with variables just like it does with my simple, 25 over here, is that I get a plus or a minus. So this particular problem becomes two problems. I'm going to show you another way to think about this in a minute that might be a little bit more straightforward. But one of the problems options is to do this, and then the other problem would be, the other part of the problem would be to do this. Is everybody good with that? One is where I set it equal to the positive part, and the second equation I set it equal to the negative part from that square root. Two questions to finish.
Why is it only positive or negative on one side of the equation?
That's a good question. If you actually had thought about it over here with the 25, the same thing happens. When we do the square root, we only put it in one place. And the reason that we do is because putting a plus or minus here doesn't give us any new information. It's equivalent. It's like saying they could both be negative. Okay, but that's the same as them both being positive, so it doesn't really matter. Yeah, you still get the same information out of them. Okay, so on the first one, what would I do? Let's call this number 1. On number 1, what would I do to solve this equation now? Okay, let me do it in 2 steps. I agree with you, Emily. That sounds like a good plan. So this would be x on the left, and then I have 2 minus x on the right. And then Emily wants me to add the x as well. So now I have 2x on the left and 2 on the right. And then what would my last step be if I got to here? Yeah, divide by 2. So x could be 1. Okay, second option over here is that I have x minus 1 equals, and this says negative 1 plus x. What was that? Yes, I distributed the negative. So that's how I got the negative 1 plus x. Now what? Ooh, they do. So if I try to move an x, all of a sudden I end up with this statement. Samantha's exactly right. Is that a true statement? It matters, because if it's false, we get a different answer. Is it true? It's true. So if it's true, what that means is that x, whoops, is any real number. Any real number will work. So which solution, well, I shouldn't say it that way. If you take a look, these are both solutions, but the second solution actually already includes that one, right? Agreed? So what is my answer? Well, my answer is the second one that I just got. X is any number, any real number we've been working with. If you want to be real specific, we've really been working with only integers, so it's any real or any integer. But it's true that it's any real number too. So let me go back to the original problem and kind of give you a picture of why that happened so you can see. So if we take a look back at this original problem right here, I'd like for you to notice that inside the sets of parentheses, they're exactly the same except for what? The order, right? The order is different. If the subtraction side stays in the middle, one of them is 1 minus x, the other is x minus 1. So think about what happens when we switch the order of subtraction. 5 minus 2, 2 minus 5. 7 minus 8, 8 minus 7. 12 minus 3, 3 minus 12. What happens? What's that? It creates integers. But what kind of integers specifically? What is 12 minus 3? 9. What's 3 minus 12? Negative 9. What's 5 minus 2? 3. And 2 minus 5? What's happening? You get the same number part, right? But what do you get different? The sign. It's all that differs is the sign, correct? So if I switch the order of subtraction, that's why subtraction is not commutative, isn't it? It's because when I switch the order, it changes my sign. The sign is actually different. So I'm switching the order, I'm changing the sign, but then what in this problem am I doing after I subtract? I square it. And what happens when I square values? They all become positive. So it didn't matter if it was 5 or negative 5. It didn't matter if it was 9 or negative 9. When I square it, there's no more negatives, and that's what's happening here. So any number has this possibility. It doesn't matter what the value is, because I'm subtracting it just opposite orders. Does that make sense? So that's why that's happening. Obviously, that's a very unique situation. We're probably not going to see that happen on another example, but I just wanted you to be aware that that's actually happening here for a very specific reason that I get all real numbers, is because they really are the same thing, because I'm squaring it on both sides.